Loudspeakers interfering. Two loudspeakers separated by a distance d are placed at a distance L from the y-axis. The loudspeakers generate waves with the same frequency f and amplitude a. The waves oscillate in phase. When a microphone moves in parallel to the y-axis, it can detect points with no sound or maximum amplitude sounds. A. Describe how the sound intensity I varies as a function of position x along the x-axis from the origin. Sketch the graph of this function on the axes below. Describe how the sound intensity I varies as a function of position y along the y-axis. Sketch this graph of the function on the axes below. The distance between the speakers is d equals 1.5 meters and the speed of sound is 340 meters per second. Find the lowest speaker frequency, which will yield the minimum sound intensity along the line HH. Describe how the sound intensity varies as a function of position x along the x-axis. Sketch the graph. As the distance from a sound source increases, the intensity, which is power over area in units of watts per meter squared, decreases as a function of 1 over the distance squared. So here's our equation. This is the intensity at a distance r from the source. I0 is the intensity at the source, and r is the distance from the source. And make sure you realize that's r squared over there. Plot intensity I as a function of 1 over x squared. Now we're using 1 over r squared here. That's normally used in the intensity equation to show that sound propagates in 3 dimensions as an expanding sphere. In this case, we're only interested in the x direction. So here's where the microphone starts, I equals 0, and if you were to move it backwards like this, it falls off as 1 over x squared. So the intensity is I0, the intensity right there, divided by x squared. Now describe how the sound intensity I varies as a function of position y along the y-axis. Then sketch the graph. The in-phase and same frequency sound waves from the two speakers will interfere constructively and destructively, resulting in maximum and zero amplitudes along the y-axis. Constructive interference, that is maximum amplitude, occurs where the difference in the paths that each wave travels differs by an integral multiple of their wavelength. Destructive interference, which is minimum amplitude, occurs when the path difference is an odd multiple of half a wavelength. The amplitude of the waves decreases farther from point O along the y-axis due to the greater distance that the waves from each speaker travel, as intensity is I0 over r squared. So the interference pattern is shown by the alternating maxima and minima, and the decreasing intensity is due to the distance from the source, which is I0 over r squared, right? Because if your sources are here, that's two sources, but if you're over at that point, they're much farther away. Find the lowest speaker frequency, which will yield the minimum sound intensity along the line HH. Use a destructive interference formula to find the frequency that yields the minimum sound intensity, right over here. Theta is the angle that the line segment HH makes with the x-axis. Right, there's our 90 degrees, here's the x-axis. The lowest speaker frequency corresponds with the largest wavelength. Choosing m equals 0 and solving the above equation for lambda results in the largest lambda, but the smallest frequency. So here's our first equation, and we set m equal to 0 because we want the lowest lambda, and then we put 90 degrees in here for the angle, and we find that lambda is equal to 2d. Now we use our lambda equals the velocity of sound over frequency formula and solve for f. So here it is. Rearrange it to solve for f, put in our values, and we have 2d here, and we get a frequency of 113 hertz.